All right, I wanted to go through a tricky little derivation problem with you. The idea is not that you will be encountering proofs this hard in this class in general. In fact, you won't. But I think this problem is illustrative of the kind of thinking you need to be doing in order to get through these things. So I wanted to try to give you a sense of what's in the logician's mind when he or she is trying to do one of these proofs. Okay, here's the challenge. We want to prove P from the starting premise not if P then Q. Okay? And if you think semantically for a moment about what these sentences mean, I think you'll see that in fact P must be true given that not if P then Q is true. Because if it's true that not if P then Q, well, that can be true only if P then Q is false. And we know that P horseshoe Q is false only when P is true. And in fact, Q is false. Okay. So if we have not P horseshoe Q, we ought indeed to be able to prove that P. Okay. By the way, I'm going to go through this document, and the document outlines the whole proof, but you may want to pause the recording at various moments to sort of think about it for yourself and see if you can figure out the right tactic at the right moment. Okay, well, here's how we start. We draw a vertical line, a horizontal line underneath our single premise, not if P then Q. How are we going to prove that P? Here's our first thought. We're going to prove that P by using, ultimately, negation elimination. Right? We're going to assume not P and try to derive a contradiction from that. Okay? So we'll start off like this. Right? We're going to assume the opposite of the thing we're trying to prove, hope to get a contradiction, and then we'll have our proof that P. All right. Well, how are we going to get a contradiction? You may want to pause the recording now and think about this for a second. Okay, how are we going to get a contradiction? Well, the only thing we have to work with is this, not if P then Q. So maybe we'll be able to derive from the assumption that not P, P horseshoe Q. Okay, if we could get P horseshoe Q, then that would contradict our original starting assumption, and so we'd have a contradiction from not P, which would allow us to conclude, via negation elimination, P. Okay? So what I'm now thinking is this. We'll assume that not P, derive a contradiction, which contradiction will look like this, and then we'll be able to conclude that P. Okay? Well, now the question is, how are we going to get if P then Q from our assumption that not P? Again, you may want to pause for a moment and think about this. Okay, if we're going to prove if P then Q, then that strongly suggests that the rule we'll need is horseshoe introduction, right? Implication introduction. And in order to use that, we have to make an assumption, namely of the antecedent. That is, we have to assume that P. Okay? So now my thought has evolved into this picture. The picture looks strange because we've assumed not P and now we're assuming P on top of that, right? But we're really just sort of forcing ourselves to use the rules as we have them. We decided that we wanted to use negation elimination in order to prove that P. That meant assuming not P. And then we decided that we wanted to use horseshoe introduction for our proof that if P then Q. And in order to use that, we have to assume that P. And we need to conclude, obviously, that Q. Okay? So now our challenge is down to this. How shall we prove Q from P? Okay, again, you may want to pause the video and stop and think about this for a moment. Our challenge is to prove Q from P. Well, again, the natural move to make is to think, well, if we could get a contradiction from not Q, then we'd have our proof that Q. Okay? So we're thinking we'll make yet another subproof. Okay? We'll assume that not Q, we'll somehow get some contradiction, then we'll be able to conclude that not Q, which will give us a proof of Q from P, So that will entitle us to conclude if P then Q, which will contradict our original assumption, which will give us P ultimately, finally. Okay, well now there's one more task. How shall we get a contradiction from not Q? Okay, again, pause the video, think about this before proceeding. The question is how to get a contradiction from the assumption that not Q. Well, in fact, this is pretty easy. We've already assumed both P and not P, right? And those, of course, are contradictory. So all we have to do now is to reiterate those assumptions, and we'll be done. Okay. So here's the completed proof. From the assumption that it's not true that if P then Q, we assume not P in order to start off a negation elimination, which will ultimately conclude that P. Then we assume P with the goal of producing this sentence, if P then Q, by horseshoe introduction. And then we make the further assumption that not Q, with an eye toward using negation and elimination inside, in here. If we get a contradiction from not Q, then we'll have our proof that Q from P, etc. And in fact, the contradiction from not Q is pretty straightforward. Since we've already assumed P and not P, we can just write those down again. Contradiction, therefore Q by negation elimination, therefore P horseshoe Q by horseshoe introduction. And now, since we have a contradiction, by negation elimination, we can conclude finally that P. Okay, and that's the proof. That's it. Somewhat complicated. It looks nasty because of all the subproofs and because of the sort of counterintuitiveness of assuming not P and then P, especially when P is the thing you want to prove and so on. But the thing to keep in mind is that we are forcing our proof to obey the rules as we understand them. Right? We really only have a few different rules that we're entitled to. And we're just forcing our proof to fit those rules, right? How are we going to prove that P? Well, the only thing that looks plausible is negation elimination. So we have to assume not P. Now we need to get a contradiction. How are we going to get a contradiction? Well, most naturally we'll be able to prove P horseshoe Q from not P. And notice, again, semantically, if not P is true, then indeed P horseshoe Q will be true. Right? How do we do that? Well, we're going to have to use horseshoe introduction, which means we're going to have to assume P. Okay? How do we prove Q? Again, it looks like the only reasonable method to use is negation elimination, so we'll assume not Q. That gives us a way to reach a contradiction, so we can conclude that Q. Then we can close that subproof and conclude that P horseshoe Q. Then we can close that subproof and conclude by negation elimination that P. Okay? That's a tricky one, but I think it's illustrative of the kind of thinking that needs to happen if you're gonna be able to solve these tricky little proofs. Again, you won't see any of this hard on the exams, but as you're going over the exercises and preparing for exam 2, I hope this will be helpful to you as you attack these things. All right, thanks.